the Pigeonhole Principle 3. Let's look at another version of Pigeonhole Principle. First, let's look at this example. There are 3 pigeonholes. If some pigeonhole receive at least 5 pigeons, then at least how many pigeons must be there? And this one, if we know when some pigeonhole has a number of pigeons, then how many total pigeons must be there? It's different from the previous version. The previous version is, we are given a number of pigeons and a number of pigeonholes, then we can be sure some pigeonhole receive at least 1, which means there are 2 or more. So here, if we know some pigeonhole has at least 5, then how many pigeons must be there in total? So it's a different version. So remember the pigeonhole principle, we mentioned that before. So in this case, the set is pigeons. And then the cardinality of this set is the number of pigeons. And then here, we have k categories. That means k equals 3 pigeonholes. So then the average of each category, or the average of each hole can receive, is the cardinality divided by k, as we indicated before. So in this case, then we expect it's be greater than or equal to 5 because it says at least 5. But now, and we can also use greater than 4. If this is 4 point something, then it must be 5 to keep the whole number. So consider this. Then you multiply by k, so you get 4k. So then, therefore, and if it plus 1, this is the minimum number it must have. So in our case, then we have 3. So this will be 4 times 3 plus 1, so there will be 13. So this means if, at least there are 13 pigeons there. So for this version of Pigeonhole Principle, and we can state a general statement here. So here's the second version. The Pigeonhole Principle second version suppose that objects are to be distributed into n categories. To ensure that some category receive at least m objects, we must have 1 plus n times m minus 1 objects. So like we have in the previous example. So if this one would be like m equals 5, and then we have 3 objects, 3 categories, then the total number will be, 1 plus 3 times 4, so that is 13. And let's look at another example, and the next example is also in the book. If Ed's sock drawer contains 7 blue and 12 black socks, unfolded and unsorted, how many socks must Ed draw at random to be sure of getting A, 6 socks of one color, B, 6 blue socks, C, 3 matched pairs, possibly including pairs of each color? So here, unfolded and unsorted. This one, it just means when Ed draw from the drawer, and it will be random, so it will be completely blind draw. Okay, that's the purpose we stated here, unfolded and unsorted. So question A, and there are 2 categories actually here, so there will be blue and black. That are 2 categories, so into n categories. And then to ensure that some category receive at least m objects. So here we talk about 6 objects. So m equals 6, and then n equals 2. So we have 2 categories. So by the Pigeonhole Principle, the second version, then the total number we need will be 1 plus n times m minus 1. So it will be 1 plus. So this will be 2 times 5. So that 11. So in this case, we need 11 socks. So that we can guarantee, 6 in the one color. And let's look at B. In this case, actually the Pigeonhole Principle does not apply. But we use the worst case analysis. So we want to draw 6 black socks. So when you look at, we could draw all blue socks before we get a black. So therefore the worst case will be we get 7 blue, and then after that we can get all the blacks. So therefore the worst case analysis is we get all 7 blue socks first, and after that then we will get black socks. So therefore we need 6, so that would be 7 plus 6 is 13. So in this case we need 13 socks to guarantee 6, at least 6 black socks to ensure 6 black socks. To get 3 matched pairs, so this one, 3 matched pair means, we have a pair of one color. So maybe 1 pair is black, 1 pair is blue, or 2 pairs is black, or 3 pairs are black. We don't know, but just 3 matched pairs. So now here we have 2 categories, blue and black. So therefore, by the Pigeonhole Principle, if we draw 6, we can get 2 matched pairs, right? So by the Pigeonhole Principle, first we take 6 socks, then we can get 2 matched pairs. Because in fact, 3 socks will give us 1 matched pair. So 6 socks. So you can have 2 group of socks. So each group has 3 socks. That gives us 1. So 6 will give us 2 matched. And then we still have 1 unmatched. So if that, the worst case, so that gives us 2 matched pairs. So then we left with 2 socks. If they do not match, that's the worst case. So the worst case is that the rest 2 socks do not match. So in this case, we need 1 more sock to go with this 2. So then 3 socks will give us a pair of color, right? So then we add 1 more sock. Then with 3 socks, we get the 3rd pair. So therefore we need a total of 7 socks to get 3 matched pairs. Let's look at one more example, and this example is also in the book. Suppose 30 ping pong balls are numbered from 1 to 30, placed in a large box. A, show that if 18 balls are drawn, there must be a pair among them whose sum is 35. By sum, we mean the sum of numbers appearing on the ball. B, how many balls must be selected to ensure a pair whose sum is 40? So, and now we have 30 ping pong balls, And now we just need to create some categories. Then we can apply the pigeonhole principle. So, and then to create categories, now our goal is to prove, the sum is 35. So that means, a pair. So you put a pair of ping pong ball together so that to calculate the total, that will be 35. So now let's create 30. So let's create because we talk about 18 balls are drawn. So then we create 18 holes. So we go this way, and the first hole, just a single ping pong ball with number 1, and then the second hole, the second category is ping pong ball with number 2, and number 3, and number 4. But then we put 5 and 30, because 5 plus 30 is 35, and then we put 6 and 29. That gives us 35. 7 plus 28, and so on. So the last one would be 17 and 18. So here there are 17 categories, and then we have 18 balls. So by the pigeonhole principle, at least one category has 2 balls, and then we can place, the 2 balls in this way. Therefore, and if we get 18 balls distributed such that at least 2 balls will fall in this category. So therefore, and we just need to get, so we just need 18 balls, okay? So 18 balls can ensure a pair of ping pong balls with a sum of 35. Similarly to for question B, and now we want to have a sum of 40. So now if you look at the ping pong ball with number 1, that does not make 40 with any ball. Number 2 does not make 40 with any. Number 3 does not make 40 with any. Until number 9, it still does not make 40 with any, right? So what it can make is number 10 with 30, and then 11 with 29, that can make 40. 12 match with 28, that can make 40, right? So, and then until, 19 and 21, that can make 40. And of course, number 20 does not make with another one with 40 because you do not have another 20. So here, how many categories we have? We have 20 categories. So to ensure one category has more than 2 ping pong balls, we need 21 balls. So we need 21 ping pong balls that can ensure a pair, okay, of a sum of 40. So these are the examples we've explained and selected from the book. And you should be able to do homework in this section. The homeworks are page 75 to 76, number 7, 9, 10, 11. Thank you.